G'day everyone, welcome to Lubrication Experts, and today we've got a very pertinent topic. Today we're going to be talking all things environmentally acceptable lubricants with Dr. Ruchi Bakshi, as well as John Perez from Fuchs. I think this is the first time we've had anyone from Fuchs actually on the channel, so very excited to have the two of you. So both of you, welcome.
Ladies
Thank
first.
you.
Yeah, Dr. Ruchi, would you mind maybe just giving a little bit of an explanation of what it is that you do at Fuchs?
Yeah, hi. So my name is Dr. Ruchi Bakshi. I'm working at Fuchs in US from last 9 years. My role is in R&D as a scientist, handling industrial oil, gear oils, hydraulics, EAL, which we will be talking today. And it's pleasure to be here.
Yeah, awesome. Thank you. And likewise, John.
First, thank you for having us. It's a pleasure to be here. My name is John Perez. I work for Fuchs Lubricants Canada. I work as a product manager. Been with the company since 2008.
Oh, awesome. Okay, so two very well-credentialed people to talk us through EALs, which is frankly a gigantic topic. So, if you as the listener have a very, very specific question, there is a chance that we won't get to it. But, it's in terms of broad overviews, hopefully we'll hit all of the sort of like the major points. So we'll get stuck into it. And I guess the first and most obvious question for EALs, which obviously stands for Environmentally Acceptable Lubricants, um, what makes a lubricant, you know, environmentally acceptable? So obviously there's a range of different test criteria, you know, all the OECD type stuff. I think 301B is the one that I typically see on the data sheet. Um, but is there anything that let's say the entire industry has agreed on that makes something an EAL?
Thank you for your question, Raf. So the lubricant should be readily biodegradable, which means it is a measure of a breakdown of a chemical or a chemical mixture, breaking component, the active group to inactive so that it reduces the toxicity for the microorganism, aquatic microorganism. It should have low tendency for bioaccumulation, which means, as I said, changing the active component to inactive component so that it reduces toxicity and the toxic materials which is going in the water for the aquatic life. So the overall, if we are talking about the overall broad overview, this should be the criteria. The oil or the lubricant should be biodegradable, should have low toxicity to the aquatic organism, low bioaccumulation. And there are various tests which we do, as you mentioned, OECD 30B, OECD 2001, or OECD 107 and 117.
Yeah. So with all of those tests, and I know that let's say for example, there's readily versus inherently biodegradable and all this sort of stuff. Is there kind of like a consensus on you know which one is the standard, or if we meet the criteria for any of those tests, does something become an EAL?
So, if I may please, so the standard really is readily biodegradable. So inherently biodegradable has a range, and then readily biodegradable is a range. So for it to be readily biodegradable, it needs to be 60% biodegradable within 28 days as per OECD 301B. So that's one of the things that you need to consider when you're qualifying EAL, because there's a lot of advertisement in the marketplace for that, and some people could be misled that they're thinking they're using an EAL product because it will write biodegradable. But different fluids have three types of biodegradability: non-biodegradable, inherently biodegradable, and readily biodegradable, right? So for EAL, first it needs to be readily biodegradable. And then on top of that, like what Dr. Bakshi said, it needs to be also low aquatic toxicity and low tendency for bioaccumulation. So those are the three things that you need to watch out for: readily biodegradable and those other two tests.
Yeah, that's really interesting because that's one of those areas where I know, my experience working in the field here in Australia is that often, everyone has a different reason for purchasing, an EAL style product. In some cases, I've experienced like a lot of end users. Realistically, all they're looking for is the word bio in the product name, right? And that basically so that they can tick a box and say, we've gone to the effort of trying to source a bio product. Versus there are others who have a strong intent to ensure that any product which ends up in a water stream or something like that,
Yeah.
Is not dangerous in the long term. So there's definitely a very broad range of end use cases. Maybe just to pick up on one of the specific terms that you guys were talking about, though, was because I think, low toxicity, I think is someone that maybe everyone kind of has an intuitive understanding of toxicity. But would you mind just maybe expanding a little bit more on what that term bioaccumulation means?
It's the tendency of a substance to bioaccumulate. Bioaccumulation is the buildup of chemicals within the tissues of an organism over time. The longer the organism is exposed to a chemical and the longer organism lives, the greater the accumulation of the chemical in the tissues. If the chemical has a low degradation rate and low depuration rate within an organism, concentration of that chemical may build up in the organism's tissue and may eventually lead to adverse biological effects.
Right. Okay. So is that kind of like the idea of, I'm trying to put it in very simple terms for people. When you talk about heavy metal accumulation, let's say, for example, in fish species, and everyone's always concerned about how much, I don't know, mercury they're eating when they eat their tuna, sort of thing. We're seeing the same build-up potentially of, chemicals, let's say, for example, that were in lubricant additives that, could potentially can be passed down through generations of fish species. Is that the sort of thing that we're talking about?
Yes, same idea. Fish eats heavy metal, it accumulates in their tissue and could make it all the way to our dinner table. Another way of thinking about it is that it could go up the food chain to higher mammals, including us.
Okay, that's very helpful. And maybe we're getting a little bit too far into the weeds here, but um, just in terms of bioaccumulation, for example, is this where the conversation around a lot of those sort of PFAS style additives seems to be kind of circulating? And so I know people might know them by that term, the forever chemicals, and I know Fuchs has been pushing pretty hard to remove any traces of sort of like PFAS or PFAS derived products from a lot of its formulations. So is that sort of where that conversation leads?
So I think what you're trying to get at is what's the spirit of it. So for
Yeah.
bioaccumulation, is we just the idea behind it is you're trying to prevent, going up the food chain. So say for example, there's a leak in the marine application, and you from the bottom of the food grade all the way to us. So that's exactly what we're trying to prevent.
Yeah, awesome. Okay. Thanks
Mm,
for that, because I think there's a lot of misnomers about what all of those different terms mean.
yeah,
And so
yeah.
getting people straight on what I'm looking for is an inherently biodegradable product, low toxicity.
Readily biodegradable.
Oh, readily biodegradable.
Yeah,
There you go. Even I get it wrong.
yeah,
Readily biodegradable, low toxicity, low bioaccumulation.
yeah.
All of those things kind of makes an EAL. So once we've established like what an EAL is, um, what kind of base stocks would we typically see in sort of an EAL product? So from an end user side, we're often interested in making sure that we've got compatibility with existing products if we're doing a switchover. So maybe John, from an application standpoint, you know, are we expecting to see anything exotic, or is it some of the base stocks that we are pretty familiar with?
Nothing exotic per se. Base fluids are triglyceride, synthetic esters, polyglycol, and polyalpha olefins. Triglycerides, for example, are canola oil, rapeseed oil, sunflower, and soybean oil. Most of the end users are also familiar with other product group such as PEG, PAOs, since they counter these chemistries in different applications. John, do you want to add anything?
typical use right now for EAL, like conventionally would be your triglycerides, like what Ruchi said, their canola oil, sunflower oil, or soybean oil. But if you want to increase the performance advantage from conventional chemistry, mainly because they have limitations compared to mineral oil, for example, hydrolytic and thermal stability, especially in the presence of water, then you could definitely move up to different types of EAL. Your PAO, for example, there's certain types of EAL that's PAO, polyglycols, or even the synthetic esters. So it depends on the applications that you're looking for.
Yeah, that's really interesting. So maybe it would be helpful to explain to people how we accomplishing the breakdown of such a broad range of base stocks, right? Because I think in a lot of people's conception, some of those base stocks are almost like the opposite of each other. So I think, when we explain EALs, for a lot of people, it's very easy to understand how a triglyceride or an ester could be an EAL because they see the hydrolytic, let's say, instability of an ester as being an advantage when it comes to, um, you know, biodegradability because, you mix it in with the presence of water and the molecule itself will break down and obviously devolve into, your alcohols, for example, and your acids. Um, when we talk about sort of, especially PAOs and PAGs, they seem to be so stable in the presence of water. So how is it that they are actually breaking down in the test?
So the test is OECD 301B. So the idea behind it is you introduce the substance inoculum. Microorganism degrades the polymeric structure. It degrades back to its base monomers.
Yeah.
Okay, cool. So that's helpful to know, right, as well, because it sort of, from a formulation standpoint, obviously it constrains the box a little bit. Um, yeah, so that's very helpful to know. So, just in terms of applications, uh, if we're discussing where EALs have historically been used, um, you know, I think the obvious ones are anywhere where you need like a drinking water source. So here locally, I do a fair bit of work with kind of like the local water authority, um, and that's an obvious place. But where are some of the use cases that you've seen where an EAL is either required due to some kind of like regulatory reason, or um, there's a strong push from the company itself to use an EAL?
So at least here in the North America, US, Canada, we see it required in marine applications, mainly because you have high tendency of leakage into waterways. So it's almost regulated for us. I shouldn't say almost regulated. It is regulated for us. And then typical applications that you would see it would be construction, mining, forestry, waste collection, utility, bridges and dams and locks. So it's heavily used when it's regulated. And then it's also heavily used if there's significant exposure to market perception in terms of leaks. So waste collection fleets, for example, they go through residentials. And you can imagine if there's significant leak for those fleets, you could see it on the ground where there's quite a bit of pedestrians. And that's when they would typically use EAL as well. On top of that, reclamation is extremely expensive. So in places where reclamation could be very significant, they tend to use environmentally acceptable lubricant as well.
Yeah, and maybe a question about, the intended use. So if I can take an analog to, let's say, the food grade world. So in food grade, although we have, NSF H1 style lubricants, there is still a responsibility on the owner to minimize exposure to the product, right? Because,
Yep.
whatever the acceptability limit is, I can't remember, it's like 1 in 10,000, something like
BPM or
that. Yeah,
something like that.
yeah. So the idea is, although we are making the product as safe as possible for exposure to food, it's still the responsibility of the operator to ensure that there is minimal exposure. Now, in the realm of EALs, is the aim still to minimize any kind of leak to the environment, or is it viewed as these products are safe to leak into the environment?
So the general it's safe to leak into the environment. But essentially, you don't want that in your equipment anyway. Mainly because if your equipment is leaking lubricant, then you're gonna have low volume, and that's another problem on itself, right? But the idea behind it is that the onus is on the operator to for his diligence to make sure it's as safe as possible. But if it does happen, then it's safe for the environment.
Yeah, cool. And then maybe one other question around sort of like the testing criteria, because um, you know, you mentioned marine applications is obviously an area where this is strongly used, and
Yeah,
you know,
dockside or on vessels. Yeah,
yeah, and think of like stern tube lubricants, for example, which have some
right.
kind of
Yeah,
permanent exposure to the environment. So that's an obvious, very obvious use case for it. But something that often will crop up on the technical data sheets is you see this term VGP, or vessel general permit. Um, Now, we spoke a little bit about the marine plus regulatory. For people that are not involved in marine, what is that VGP, and how does it relate, for example, to some of the testing that's done?
VGP stands for Vessel General Permit. You have VGP and SVGP. So S stands for Small Vessel General Permit. So these are products that are approved for on-vessel application. Similar requirements, you want readily biodegradable, low bioaccumulation, and low aquatic toxicity. The idea behind it is you want environmentally acceptable lubricants that have little or very low adverse effect to aquatic life.
Yeah, awesome. Okay. So now that we've kind of like talked through that, all the different applications of it, maybe a question, sort of another obvious question is, what limitations do EALs impose? There's sort of two different ways to ask that question. Maybe the first I'll put to Ruchi, which would be, what kind of limitations are there from an R&D perspective? We talked very, very briefly just earlier that it kind of limits the formulation box in terms of the types of base oils that you can use, but also maybe extend that further to additives, or the way that the testing has to be done. How restricted are you from an R&D perspective?
First limitation is cost, and second is availability. Mineral oil is very economical base fluid and is widely available. Other limitations are based on base oil type. Natural and synthetic esters typically have poorer hydrolytic and oxidation stability compared to the mineral oils, especially API group 1 and group 2. PEG has material and paint compatibilities, incompatibilities. PAOs have low solvency. Last but not the least is toxicity. Natural esters are vegetable oils such as canola oil, rapeseed oil, soybean oil, and sunflower oil. These are also high oleic versions of There are also high oleic versions of these vegetable oils to provide high oxidative and hydrolytic stability, whereas synthetic esters are manufactured compounds from esterification of alcohol and carboxylic acid. Synthetic esters provide much superior oxidative and thermal stability compared to the natural esters, which means longer service life interval and more resistance to varnish and sludge formation. On the other hand, cost is more economical for natural ester, which is a big factor for many end users. We are doing significant research on high oleic canola, sunflower, and soybean oil, and our current finding is that it's a great balance between the cost and the performance.
I guess there's always sort of a natural trade-off there.
Yeah,
Is
yeah.
that the term that people should be looking for? Because I think a lot of end users don't have sort of the depth of knowledge to be able to read through all of the different criteria. Is that one of the things that they should be looking for on a data sheet? Is that either the term natural or synthetic ester, for example, to be able to distinguish? Um, I don't want to say exact levels of performance, but in broad brushstrokes, what is the philosophy behind the product?
So
So right now, because market is going towards biodegradable sustainability.
Mm.
So this is one of the main criteria when we are introducing any new raw material or looking to improve the performance. Let's example, we have a existing EAL lubricant and we are trying to enhance the performance of that. So one thing what we are trying to do, we are moving towards, like example, existing formulation contains canola oil, sunflower or soybean. We are moving towards high oleic soybean. So that will enhance the oxidative and hydrolytic stability of the base stock as is. We are trying to evaluate the additives which are compatible with those. So market is also working towards those additives. It's just we have to test and prove that b- without increasing the cost, we can improve the performance.
Mm.
So these are the criteria where we are working on, because if we choose synthetic esters based on natural, of course the cost will go high. So not moving towards the synthetic, we are trying to work, and the market is also trying to work towards high oleic. So in the data sheet, we are really looking if the fluid or the base stock is 80% or more biodegradable,
Yep.
or the source is biodegradable.
Yeah, interesting.
So
Interesting. Oh, sorry.
if I add then, so say for example you're a buyer and you're looking at the product information sheet or the safety data sheet. It's more implied in the product information sheet for a particular commercial good. So if you want to differentiate between different types of EAL, between ester, most people would classify will put synthetic if it's synthetic. So between HETG, which is triglycerides, your natural esters, and then your HES, your synthetic esters, the way you see that on the product data sheet is the specification. One would write HETG, the one would write HES, and the other one most likely will write synthetic esters if it's synthetic ester, or if not, they'll just say vegetable oil, natural source ester, or even say the actual word canola oil, soybean oil, or sunflower oil. Between polyglycols and PAO, then they would just say it's probably synthetic. And the way you could see it again is on the specifications. You'll see EHEPG or HEPR, but a lot of the times you could also tell it on the specification on the typical properties of the fluid.
Yeah, and when you're referring to something like HEES or HEPR, just to clarify, those are the ISO classifications, right? For let's say hydraulic oils.
Correct. That's
So
the
different types of hydraulic oils. So that's kind of like the broadening out of if you see something like HLP, HVLP, right? This is the extension of that into kind of the realm of synthetics and understanding if it's an ester or a polyglycol. And obviously, there's also classifications for hydraulic phosphate esters, but that's not part of the biodegradable range. So,
HFDR and the HFDs. Yeah.
yes, yeah,
Yeah.
exactly. So, maybe so now we've kind of understood the limitations from an R&D perspective. Maybe John, you could help sort of inform a little bit in the field. What are the limitations that we have when we're using EAL products as well? You know, as an
So
end user, are we kind of like constrained in any way?
So with the natural esters, for example, with the HETG, with the triglycerides, the biggest limitation for application use is their thermal stability, oxidative stability, and hydrolytic stability. I mean, API group 1, group 2 base fluids, group 3 base fluids, those have certain oxidation stability, and the group 2 and the group 3 are fairly good if you're looking at hydraulic fluids that are group 2 and group 3. But when you compare that to a triglyceride, for example, it's not even as good as a group 1, mainly because canola is not that stable in terms of oxidative thermal stability compared to those mineral oils. So that's the biggest limitation, is service interval for triglycerides. Now for synthetic esters, then it's definitely improved. Then at least we can see much better oxidative and thermal stability. With the polyglycols, the biggest limitations would be the compatibility, seals and gasket, pin compatibility. That's the one that you need to look after. The biggest restriction with polyglycol is the cost. Obviously, it's one of the most expensive out of those four, right? PAO is one of the best ones. I mean, with synthetic PAO, it's got good compatibility with mineral oil. It's got good compatibility with existing conventional seals and gaskets. So the only restriction I would see with PAO is mainly the cost.
Yeah, interesting. Interesting. Um, Maybe just as an aside, for whatever reason, the PAO style, um, EALs seem to be somewhat rare in the market. Um, it feels like, as an end user anyway, that the market is dominated by the natural and synthetic esters. Is there a R&D reason, um, Ruchi, why that might be the case?
Cost and regulations.
Oh, it's okay. Back to cost.
Yeah.
Okay.
So the main criteria is cost.
Okay. Interesting. Um, cool. So we've obviously this entire conversation is kind of focused around, you know, sustainability in the sense of, we're looking at these products and looking at trying to minimize risk to the environment. Are there any other sort of like side benefits? Because I know a lot of businesses at the moment are looking to improve their sustainability performance by any means necessary. So are there any other benefits conferred by the use of EALs which businesses can take advantage of?
No, absolutely. So the biggest one is to reduce operational product carbon footprint or PCF. So many countries, the US, Canada, Australia, you have net zero targets, whatever year that would be. And one of the ways where you can actually reduce your PCF is through the use of environmentally acceptable lubricant, because compared to conventional products, they definitely have lower PCF value. On top of that, any EHS program, you want to protect the people that that's working for the company, right? So EAL are generally non-toxic, non-hazardous, so it's definitely safer to use for personnel as well. And on top of that, I mean, PAO, for example, polyglycols, for example, synthetic esters, they definitely have some efficiency improvement, and we could talk about that more in detail, but there's definitely some efficiency increase that way as well. And the last thing is just your corporate goals. If you have corporate goals to be sustainable or more as a better corporate citizen, you can use EAL type products because they're sustainable and renewable.
Yeah. Okay. That sounds, to be honest, there's so many benefits that I can see. At least there's a bit more of a push in the marketplace to use these more and more, which means potentially, a lot more funding for like development of these products, because the regulatory environment is shifting, the corporate environment is shifting, and I do see a lot more requests for bio style or EAL products. So as we start to wrap up these conversations, I always like to ask a question about the future of the category, and so broadly speaking, Ruchi, where do you see the development of EALs kind of going next? Maybe sort of like in the near term and medium term future.
Definitely, it's increasing. We have our own internal KPIs to accommodate sustainable products such as EAL to future uh, product portfolio and to align our offerings with major OEMs.
Yeah, awesome. Um, yeah, I guess that's something that we didn't really talk about was the development of sort of the high viscosity fluids. Um, and maybe you could elaborate just a little bit on the challenges of some of that, because my understanding, this is my very very basic understanding here, is
Mhm.
that uh, Mother Nature seems to love to build carbon chains that are like 16 to 18 carbons in length. Um, Now, length of carbon chain is directly correlated to viscosity. So if you have a very narrow viscosity range, most of the time you're playing at the lower end when you're constructing natural esters. So how do you take something which has a naturally very low viscosity and make a high viscosity, let's say EAL gear oil?
There are additives which enhance viscosity. These additives are either biodegradable VI/VT improvers or long chain synthetic esters. They are called viscosity index improvers. We are using those, and also we are working towards getting evaluated more and more biodegradable, or the source should be biodegradable or sustainable.
Yeah, cool. And I guess that speaks a lot to sort of the future additive developments as well. John, do you have anything to add from kind of like the application side of what you see over the next sort of, let's say, 5 to 10 years?
5 to 10 years, 5 years is a little bit hard because this one is really heavily regulated, right? So most people would stick to conventional mineral oil, conventional synthetic, mainly because those are proven product with high volume economical costs, right? So in the next 10 years, I think there's going to be a stronger push, mainly because each country is going to have to aim towards their net zero targets. So I would see this not so much in the short to medium term, but in the long term, there's going to be a lot more interest in it. As the countries reach their net zero target, there's going to be more and more push for these type of products because it will reduce their PCF contribution.
Yeah, yeah, interesting. All right. Well, both John and Ruchi, thanks so much for joining us here today. The information that you provided going to be invaluable, and at some point, I'll have to get you back on the podcast for round two on a different topic. So, really appreciate your time, and yeah, we'll talk soon.
Thank
Thank you.
you.
Thank you for having us.